Gold, the very word shines. For millennia, humans have cherished this remarkable metal. We have adorned our bodies with it, built monuments with it, and even fought wars over its possession. Gold symbolizes wealth, power, and beauty across countless cultures. Its resistance to tarnish, radiant luster, and sheer rarity have made it a universal standard of value. The dream of finding gold is not confined to our planet Earth. As we gaze up at the vast, star-studded expanse of the cosmos, a tantalizing question arises: could there be gold out there, waiting among the stars? The idea of mining asteroids or distant planets for precious metals like gold has long been a staple of science fiction. But as our understanding of the universe deepens, this dream begins to touch the realm of scientific inquiry. The scientific quest to understand where gold truly comes from is a fascinating journey in itself. Gold is a heavy element. Forging such an element requires energies and processes far beyond what Earth's geology can provide. Our journey to find gold in space starts with understanding these incredible cosmic forges. Our quest for cosmic gold leads us to some of the most extreme objects in the universe. Among these are neutron stars. Imagine a star much more massive than our Sun reaching the end of its life. It explodes in a brilliant supernova, leaving behind an incredibly dense core. This core is a neutron star. Within this family are magnetars. Magnetars possess the most powerful magnetic fields ever detected. These fields are 1,000 trillion times stronger than Earth's. They announce their presence through dramatic bursts of X-rays and gamma rays. To understand a magnetar, we must first understand its dramatic origins. It all begins with a massive star, a star many times more massive than our own Sun. These giants live fast and die young, burning through their nuclear fuel at a prodigious rate. For millions of years they shine brightly, fusing lighter elements into heavier ones in their scorching cores. But this process cannot go on forever. Eventually, the star builds up an iron core, and iron fusion does not release energy, it consumes it. When the iron core grows too massive, it can no longer support itself against the crushing force of its own gravity. In a fraction of a second, the core collapses catastrophically. This collapse triggers a monumental explosion known as a supernova. From the ashes of this stellar explosion, if the original star was massive enough but not too massive to form a black hole, a neutron star can be born. The core collapse crushes protons and electrons together to form neutrons, packing the mass of 1.5 suns into a sphere just a few miles across. This process supercharges the neutron star's magnetic field to the extreme levels that define a magnetar. The defining feature of a magnetar is, without a doubt, its magnetic field. If a magnetar were as close as the moon, its magnetic field would wipe every credit card on Earth. It would pull the iron from your blood. The energy locked within this magnetic field is immense, far exceeding the energy of its rotation, which powers more common neutron stars like pulsars. This magnetic energy is the source of all the dramatic phenomena we observe from magnetars. The field exerts incredible stress on the magnetar's crust, which is thought to be a solid lattice of atomic nuclei and electrons. As the magnetic field evolves and sometimes reconfigures itself, it can twist and strain this crust. Eventually, the stress can become too much for the crust to bear. It cracks. It breaks. This is a starquake, an event on a magnetar analogous to an earthquake on Earth. When these starquakes occur, or when the magnetic field lines in the magnetosphere suddenly reconfigure, enormous amounts of energy are released into space. This energy often takes the form of intense bursts of X-rays and gamma rays, the most energetic forms of light. Giant flares from magnetars are among the most luminous events in the galaxy, briefly outshining all other X-ray sources combined. Let's return to our quest for gold. We know it's not made on Earth. The early universe, born from the Big Bang, was almost entirely hydrogen and helium, with trace amounts of lithium. All the other heavier elements on the periodic table, including the carbon in our bodies, the oxygen we breathe, and the silicon in rocks, had to be forged later. The primary factories for these elements are stars. Through nuclear fusion in their cores, stars convert lighter elements into heavier ones. Stars more massive than the Sun can continue this fusion process, creating progressively heavier elements: carbon, oxygen, neon, magnesium, silicon, and finally iron. But what about gold, platinum, silver, and uranium? These are much heavier than iron. To create elements heavier than iron, especially the very heavy ones like gold, a different kind of nuclear process is needed. This is called the R process, which stands for rapid neutron capture. The R process requires an environment with an incredibly high density of free neutrons. In such an environment, atomic nuclei can rapidly absorb many neutrons before they have a chance to decay radioactively. This event provided strong evidence that neutron star mergers are a primary site for the creation of gold in the universe. If neutron star mergers are cosmic gold factories, where do magnetars fit in? Could supernovae that create magnetars also produce gold? Supernovae are extreme and produce some R process elements but might not account for all the gold. Magnetar-forming supernovae are energetic, possibly hypernovae. These could create better conditions for the R process. Magnetars' intense magnetic fields and rapid rotation might be crucial. However, their precise yields are still debated. Magnetars might not be primary gold producers like neutron star mergers, but their extreme environments could still play a role. Their activity, winds, and flares influence element distribution. Studying magnetars helps us understand neutron-rich matter. This is crucial for modeling R process environments. When we talk about neutron stars, magnetars are not the only kind that capture our imagination. Another famous type is the pulsar. Both magnetars and pulsars are rapidly rotating, highly magnetized neutron stars. They are essentially cosmic siblings, born from the same supernova process. However, despite their shared heritage, they exhibit remarkably different behaviors, primarily due to one key distinguishing factor: the strength of their magnetic fields. Pulsars are like cosmic lighthouses. They have strong magnetic fields, typically 1 trillion times stronger than Earth's, but significantly weaker than a magnetar's. As the pulsar spins rapidly, sometimes hundreds of times per second, beams of radiation, primarily radio waves, sweep across space from its magnetic poles. If one of these beams happens to sweep across Earth, our radio telescopes detect a regular pulse, hence the name pulsar. Magnetars, as we've established, have magnetic fields that are typically 100 to 1,000 times stronger than those of ordinary pulsars. While a pulsar's energy output is primarily driven by the loss of its rotational energy, it gradually spins down over time. A magnetar's activity is powered by the decay and instability of its enormous magnetic field. This leads to very different observational signatures for these two types of neutron stars. Magnetars are undoubtedly extreme, but the universe has other contenders for the title of most extreme object. Perhaps the most famous of these are black holes. Both magnetars and stellar mass black holes are endpoints of massive star evolution, representing matter compressed to incredible densities. However, they are fundamentally different beasts, each pushing the laws of physics to their limits in unique ways. The most obvious difference lies in their ultimate density and structure. A magnetar, while incredibly dense, is still made of recognizable, albeit exotic matter, mostly neutrons. It has a surface, albeit one where gravity is hundreds of billions of times stronger than on Earth. A black hole, on the other hand, is a singularity, a point of theoretically infinite density, where our current laws of physics break down. What defines a black hole from the outside is its event horizon, a boundary beyond which nothing, not even light, can escape its gravitational pull. Magnetars are dense, but black holes represent the ultimate triumph of gravity over all other forces. This structural difference leads to vastly different interactions with their surroundings. If you fall into a black hole, you cross the event horizon and are inevitably drawn towards the singularity, with no surface to stop you. Why do we dedicate so much time, effort, and resources to studying these distant, bizarre objects like magnetars? They are certainly fascinating in their own right, cosmic curiosities that push the boundaries of what we thought was possible. But the importance of studying magnetars goes far beyond mere curiosity. These objects are natural laboratories for exploring some of the most fundamental laws of physics under conditions that are utterly impossible to replicate here on Earth. They offer us a unique window into the workings of the universe at its most extreme. By observing magnetars, we can test our theories of physics in regimes of incredibly strong gravity and unimaginably intense magnetic fields. How does matter behave when squeezed to several times the density of an atomic nucleus? What happens to the vacuum of space itself in the presence of a magnetic field quadrillions of times stronger than Earth's? These are questions that probe the very foundations of quantum electrodynamics, QED, and general relativity. Magnetars provide real-world data points that can confirm, constrain, or even challenge our most advanced physical theories, pushing science forward. The discovery of the connection between magnetars and fast radio bursts, FRBs, has opened up an entirely new avenue of research and a new tool for cosmology. The quest to understand magnetars is far from over.